Hey everyone, we're going to do a quick review of some physics, some basic physics that you need just to understand radiation, radiation interaction and such. I'm guessing this is a review, so I'm going to go through it pretty superficially. If there's any questions we have, keep them in mind for when we meet in person and we can discuss them further in depth. I just don't want to drag on too much about something you have already been well versed in. Okay, so a great place to start a physics discussion is with chemistry. You're going to need to have some, basic knowledge of elements and the structure of an atom to understand radioactive isotopes, understand the types of radiation that come from these radioactive isotopes. So basically, an element is an inherent building block of nature. It's something that it can be split up, but it's the first level that is unique in terms of you have protons and neutrons, they're all the same. Once they combine in a certain unique way, they create an element that is different from other combinations of protons and neutrons. It's thought that every proton is similar to every other proton, but elements are essentially different. So you hear a lot of times when you hear an element, you'll hear an element with a number after it, like cobalt 60, iodine 131. These are the molecular weights of the isotope in question. This helps differentiate, a radioactive isotope of iodine versus a form of stable iodine across, every single element in existence. But these numbers are based off of the molecular weight of stable carbon, carbon 12. It gets a little tricky with these numbers. When you say I-131, it's not exactly 131 as the atomic weight, just because they take into account different binding energies. It's that mass energy equivalence that throws some things off. It's not a very clean 131. It might be 130.93 something. But for our purposes, that round number is perfectly adequate. So this is the periodic table. There's a lot of information in here, judging just based on what column certain elements are in. For our purposes, that's not a huge necessity to understand that stuff. I don't even have a full and complete understanding of it, but it's important to know kind of where an element falls on the periodic table, just to understand its properties from a radiation protection standpoint. Classical physics deals a lot more with the world around us, forces, energy. These things on a scale that we interact with day to day are a lot easier to understand than when you get to subatomic particle physics. This is where things make a lot less sense. You have, like I said, mass energy equivalence. You have things that disappear and then appear in another place in space, and it's very complicated. But we're only going to touch on that in a very superficial way, just to understand the actions of the particles we're trying to protect against. So you have a lot of the same terms, velocity, acceleration. This all applies to subatomic particles as well. But for velocity of a photon is always going to be the speed of light, whether it's a radio wave or a microwave or a gamma wave. These all have the same velocity. Acceleration comes into play when you're talking about the production of X-rays from energetic electrons. We'll get into that a little bit later. Potential and kinetic energy being something in motion. Potential energy is just something that has mass, has potential energy, again, because that mass can become energy in the right circumstances. So this is a model of the atom. It's sort of a basic model. We now understand that the electron shells don't orbit the nucleus in such a clean spherical motion. There's really complicated electron clouds that show the probability of electron in a certain area versus another area. They're not these clean orbits. But for a lot of our purposes, it's useful just to think of it this way, because it still makes sense from a protection standpoint. It serves as a model that helps us understand where these particles are coming from, where this radiation is coming from, and the fundamental changes that are taking place in the atom to create this energy, to create these particles. I touched on the atomic units. So the atomic mass is simply just the number of protons plus the number of neutrons. Again, there's some subtleties there that change the number slightly, but when you're looking to call out a specific isotope like I-131 or I-129 or any number of radioisotopes, then just using that atomic mass number is a perfect placeholder. You don't need to get into the specifics. The atomic number being the number of protons, that is what dictates what the element actually is. That's a very important number to keep in mind, because when you have radioactive decay, you have a certain element turning into another element. So that number of protons often changes, and that's something to keep track of, because you need to know what actual element you're dealing with. So you look at some common stable elements. These are lower atomic weight elements. It's common in the lower atomic weights to have the same number of protons and neutrons. This is how you'll commonly see stable elements. And then when you have that imbalance, you see like carbon-14 will have 8 neutrons instead of 6 neutrons, and that is a radioactive isotope of carbon. It decays by beta emission. So that imbalance also gives hints as to how the actual atom will decay when it comes time to decay. So just a little more into the atomic structure. Protons, what actually give the element its name, what actually decide what the element is. They're positive in charge. The neutron is the other particle in the nucleus. It has no charge, so that means that the nucleus itself is overall positive, being orbited by that negative electron shell. Oftentimes you'll see an element or a radioisotope, or just any isotope, written in this nomenclature. So the X would be the actual is the element. It's usually 1 or 2 letters. Sometimes you have to look it up if it's some very esoteric isotope, but for the most part, you should be able to recognize the ones that are relevant to the medical world. Again, like radioiodines, F18, other PET isotopes that you'll see pretty commonly in use. The A number is the actual atomic mass, so that's just going to be the number of protons plus neutrons. And what do you know? The protons and neutrons are also listed here, so A should equal essentially Z plus N, and you'll see that it does. There are a couple of variations of an element that can have. It can have, isotones, isobars, isotopes. So these are just definitions that we have to go through. Really, the most common you're going to see is isotope. I don't really know many situations where isotones and isobars come into play. I know from a chemistry standpoint they have significance, but from our radiation protection standpoint, it's really not necessary to group together isotones or isobars. We'll go through them anyways. So an isotone it is a grouping of elements, or a grouping of isotopes that have the same number of neutrons. So you can have different elements that have the same number of neutrons, but because they have different number of protons, they can be different elements. So I don't really understand the significance of this, to be honest, but it is something that exists. I believe, again, it's more significant in the chemistry world than in our world. But the easy way to remember what isotone means is that it has an N in it. So it's the same number of neutrons, isotone. When you go on to isobar, this is going to be a collection of isotopes that have the same atomic weight. So that means that they could have a different number of protons and neutrons, but the sum of the protons and neutrons is the same. So again, you're going to be in a situation where you have different elements, but they have the same atomic weight. Easy way to remember this is atomic weight. You have bar, say that, barbell, lifting weights. So an isobar has the same atomic weight. Then we get to isotope. This is really the one that is very prevalent in radiation protection, because you need to have an understanding of all the varying isotopes of a lot of the elements that are used in nuclear medicine, used in imaging, nuclear power, just the isotopes that are generally created by the large presence of neutrons that are activating the actual materials in the nuclear power plant itself. But these are going to have the same number of protons, which means that it will always be the same element with just a differing number of neutrons that give varying characteristics to these different isotopes. So they'll have the same chemical functionality. Again, not to dwell on iodine like crazy, but from our standpoint, different iodines will behave the same in a body as, those behave like stable iodine, like any isotope of radioactive iodine will behave chemically the same, but their decay structures will be different. So that's why you see, for example, the treatment of thyroid cancer is always done with radioactive iodine, because in the body, radioactive iodine, because of its chemical structure, it goes to the thyroid. So if you're looking to image the thyroid, you might use something like I-123 because it's short-lived. It has a couple of photons, easy to image. But if you actually want to give a therapeutic dose to thyroid tissue, you would use I-131 because it has an energetic beta particle that actually can pack that radiation punch that can actually kill the cancerous tissue, whereas the I-123 is just for imaging. And then you have other isotopes like I-125 that have favorable characteristics for other functions like brachytherapy. But that's for later discussion. The chart of nuclides shows all the known isotopes in existence. You see that line, that sort of maroon line in the middle, are all the stable elements. And then the further you get away from that line, you have shorter and shorter lived isotopes. A lot of these really short-lived isotopes are, essentially theoretical. They're created in these large accelerators that, these isotopes will exist for a blip in time. They're really nothing but data. Because when you get down to 10 to the negative 12th seconds, that's essentially nothing. But they have been discovered. They are physically possible, so they're documented. But you can see that the line, as it gets higher and higher atomic weights, it starts to drift away from that proton-neutron equivalence. And really, the reasoning for that is that as you get to these higher and higher atomic weight isotopes, as you get to larger and larger nuclei, if you think about it, you have more and more protons packed into this small space. So the protons are all positive. So you need some sort of filler between these positive charges to overcome that like electrical charge that's pushing away. Like charges push away from each other. But if you have enough neutrons packed in there, the nuclear force can hold the nucleus together better than the electrical forces pushing it apart. But that's also why when you have, something like U-235 is a very unstable nucleus. That's why it's subject to spontaneous fission. That's why it's able to be fissioned in a controlled setting like a nuclear power plant, is because it's kind of on the cusp of splitting, and it only needs that little nudge to actually split, versus, something like carbon-12 or, a lot of the lower atomic weight elements and isotopes are much more stable. They're much less likely to be split in such a manner. So this is just an example. It's not a very good example because there's no differentiation between protons and neutrons, but I believe that they think the red ones are the protons. So if you look at this, you can figure out what it is. You got 1, 2, 3, 4, 5, 6 protons, and 1, 2, 3, 4, 5, 6, 7, 8 neutrons. So you have an atomic weight of 14, but with the 6 protons, that would mean that it's carbon, atomic number 6. But it's a radioactive isotope of carbon. It is carbon-14, and that tells you that it is radioactive carbon. Okay, so we're just going to run through the types of radiation very quickly. This is very important to understand because you need to understand the type of radiation you're dealing with in order to detect that radiation, in order to protect against it. So we'll just run through them all. So an alpha particle is a very large radioactive particle. It's essentially a helium nucleus stripped of its electrons. So it's 2 protons and 2 neutrons. So that makes it very massive, again, on a subatomic particle scale. But because it has a large charge and a large mass, it loses its energy very quickly, interacts very quickly. If you think of matter as sort of a sea of electrons with small islands of nuclei, so the vast majority of space is just made up by electrons. So as this positive alpha particle rips through this matter, it is drawing electrons off of all of these atoms, and that's ionizing lots and lots of atoms because they're losing these electrons. But it happens over a very short period of space because it's interacting so readily that alpha particles have a very short range. Something like a couple of centimeters in air. They can be stopped by a single piece of paper because they're just going to interact with that matter so fast. Now you get to a beta decay, which is essentially an electron being emitted from the actual nucleus. And so this electron has mass, it has charge, but it's a smaller mass than an alpha particle. It's a smaller charge. So it has a little bit more range. It interacts still pretty readily, but not as quickly as an alpha particle. So again, you have that electron that's emitted from this nucleus with energy, and it's flying through this sea of other electrons that also have negative charge. So it's pushing them, all these electrons away. The alpha particle draws the electrons to it. This beta particle or electron pushes the other electrons away. So if it gets close enough to them, it can actually ionize. It can push it with enough force that it kicks an electron out of orbit, and it creates, an ionized atom. Or it can just excite them. So it just gives a little bit more energy to a local electron that then will relax by emitting an X-ray. And that's, just sort of a cascade of radiation that can lead to dose. So when a beta particle is emitted from a nucleus, it's emitted with mass and charge. That charge comes from the fact that a neutron changes to a proton. So you have a neutral particle changing to a positive particle. So that creates, you need to sort of get rid of that negative charge to create that positive charge. And that negative charge is carried off by an electron. The charge of an electron is equal in magnitude to the charge of a proton. It's just a proton is positive and an electron is negative. So that's how that charge sort of leaves that nucleus. That neutron changing to a proton fundamentally changes the atom. As you can see in the example below, you have tritium with a proton and two neutrons. If one of those neutrons becomes a proton, suddenly you have helium because you have two protons and a neutron, or you have an isotope of helium, helium-3. So that's important because every radioactive decay has to have some sort of fundamental change of the atom itself. Another type of decay is a positive beta or a positron. So this is much the same. Positron is equal in mass and magnitude of charge to an electron. The difference is that it's a positive beta, and one of the key differences is that after that that positron loses all of its energy interacting with other electrons, it will actually combine with an electron and annihilate into pure energy. And that pure energy is in the form of two photons. Those two photons go in equal and opposite directions. So equal energy, but in exactly 180 degrees from each other. And so it's turning from the mass of the two particles into pure energy. And this is the basis of PET imaging. They have, if that happens, you have detectors around the body where this is happening. Judging on when those two annihilation photons reach those detectors, you can gauge where that decay actually happened in the body. And you can start to create an image. If there's enough positrons decaying in a certain tissue or a certain organ, you can create an image of where this radiopharmaceutical went to in the body and get a lot of useful information. So this is an actual radioactive decay process. So this also fundamentally changes the element that's decaying, but it's the reverse of the negative beta, in that a proton changes to a neutron because you're emitting a positive charge from the nucleus. So that positive charge is sort of stolen from a proton. That proton then becomes a neutron, and that positron carries off a small portion of the mass and the whole magnitude of charge from that proton. There are other forms of radioactive decay where there is not an actual particle emitted from the nucleus, but there's still a fundamental change in the atom. And an example of that is electron capture. So this is usually seen in conjunction with positron decay, with the positive beta decay, in that you have a nucleus with too many protons. So it's too positive. So it's trying to get rid of that excess positive charge. Now it could do that by emitting a positron, and that gets rid of one positive charge, or it can actually take a negative electron in the electron shell and suck it into the nucleus. And when it does that, it actually changes that proton to a neutron and becomes a little less positive. So there's no actual particle that is emitted into space. But what does happen is that because that electron leaves a gap in a higher energy electron shell, then other electrons will cascade in to fill that spot. So you have a cascade from other shells of electrons falling down. So you'll get either one or many characteristic X-rays that are essentially the energy difference between the two electron shells. So when that electron shell falls from one energy level to another, it's not changing its own mass. So the only thing that changes is the binding energy, and the difference in that binding energy is what leaves the atom as a characteristic X-ray. And then the last type of radiation that we deal with regularly, but also the most common and kind of the most thought of radiation when you hear the word radiation is photon radiation. So these are photons that have they have no mass, they have no charge, so they don't interact with matter very readily. They don't fundamentally change the atom that they're coming from. They're usually seen in conjunction with an actual decay, whether it's a beta decay, positron decay, electron capture, or any form of decay. Usually is seen, you usually have some sort of photons or X-rays that are released in this decay. Now, a gamma comes directly from the nucleus, an X-ray comes from the electron shell. There's really no energy dependence. They can both be low energy or high energy, but it's important to understand that difference between an X-ray and a gamma. So we talk about penetrative power. I mentioned that an alpha particle can't even get through a piece of paper, whereas betas, they're easier to stop. They can be stopped by a thin piece of plastic, a piece of aluminum, but then you have the photon radiation that can really get through, large thicknesses of, plastic, even of lead. You get you have linear accelerators. They have to have feet of concrete, meters of concrete, or inches of lead in order to just lower the intensity of the radiation. They don't even stop it. They just significantly lower the intensity of that radiation. So they're much more penetrative than something like an alpha or a beta. So some neutrons, we're going to discuss neutrons in a second, but neutrons are sort of a different animal. They have mass but no charge. But because they have no charge, they also don't interact very readily. Where we go? Yeah, we'll get to them. Okay, so radiation interactions, we talked about, this is a little review of what you've been talking about. Alphas, they interact very readily. They have high kinetic energy. They are moving slower than the speed of light because they have actual mass. Nothing with mass can move at the speed of light. But they get, something like a beta is small enough that it gets pretty close to the speed of light, just not exactly there. One thing that I have to cover in depth with betas or electrons is the idea of Bremsstrahlung, or breaking radiation. That's the direct translation of Bremsstrahlung. It's, I believe, a German word. But essentially, an electron, when it is accelerated or decelerated, when it is changed from its course, whether by a neighboring electron or by a nucleus, or by, essentially either one in some sort of shielding material, if it's accelerated too abruptly, there is a creation of X-rays. So from a safety standpoint, if you are, shielding a high energy beta emitter with a thin sheet of lead, you're stopping the electrons. You are effectively shielding the electrons, but you are creating an X-ray source. And those X-rays are irradiating you. So you're failing in your goal of minimizing radiation exposure. But what you want to do is use something like a plastic shield that does a less abrupt job of stopping those electrons. It'll more gradually stop the electrons over, more and more interactions that will create lower energy X-rays that have more of a chance of being stopped inside the shielding material. And that will essentially lower the dose to somebody. So that's why we always stress to the researchers that are using isotopes like P32, yttrium-90, we want them to use plastic shielding so they minimize their X-ray dose. Now, if your goal is to create a high energy X-ray machine, then you want to accelerate the very high energy electrons at a very high density target that will very abruptly stop these electrons because you're trying to get these high energy X-rays from these interactions. And that's why something like a linear accelerator has, a very dense, I think it's usually a tungsten target that these high energy electrons are accelerated at to create those, multi MeV X-ray photons that are then going to be channeled to, into a usable beam to treat your patients. So it all depends on what you're trying to achieve. All medical X-ray equipment is based off of the idea of bremsstrahlung and controlling that X-ray beam into production, or controlling that electron beam into production of X-rays. Yeah, so photon interactions, I know you've gone over these with Brian, or you're in the process of going over them. So we'll just run through them real quick as a review, or maybe as an introduction to when Brian goes through them. But essentially, you have three different options when you're dealing with photons. A photon can interact with an electron and be completely absorbed by that electron. And that would, kick the electron out of orbit and give it some excess energy to then travel and interact somewhere else. But that's called the photoelectric effect. That's when that photon is completely absorbed by the electron. This generally happens in lower energy electrons, or lower energy photons. And in the material that it's interacting with has some effect on the energy threshold. High Z materials, so high atomic number materials, generally have higher energies where they'll see the photoelectric effect. So it's not a clean cut number, but it's generally below 100 keV for photons. You don't see it as much above that. Now, Compton scattering is the same idea as photoelectric effect, except the electron does not absorb all of the radiation of the photon. So there is an absorption of the photon energy that kicks the electron out of orbit, gives it some kinetic energy to keep moving, but there will also be a creation of another photon of lower energy that carries on to then go interact somewhere else with either another Compton scattering event or potentially then a photoelectric effect because its energy has been reduced. And this is essentially the cascade of interactions that deposits energy that creates dose. And now pair production is something that is theoretically possible at or above 1.022 MeV. That is the mass equivalence, or the energy equivalence of the mass of an electron and a positron. So that's essentially where you have this energetic photon that passes very close to a nucleus, and that can spontaneously cause it to turn into matter, essentially turn into a positron and an electron. That positron will then go on to quickly annihilate into the two annihilation photons. But it's scientifically possible at this energy, but it's much more common to see it at much higher energies. But if you were to take a spectrum of the radiation inside of a Linac vault, because you're dealing with photons that are significantly higher energy than this 1.022 MeV, you would see a peak at the 511 energy inside of the Linac vault because of this pair production happening in the treatment room. There would be enough positrons that are created and then quickly annihilated into 511 keV photons that you would see that as a distinct energy. You have the spread of scatter that covers everywhere from 0 to your max energy, but you would see some distinct peaks, one of them being 511s. So this just sums up the usual energy ranges of the interactions. Again, it's a spectrum. It deals with probabilities, deals with the material that's actually absorbing the photon. But these are good rules of thumbs for the energy range that you're dealing with. We mentioned neutrons. Neutrons are created from Linacs, so something we have to keep in mind. It's actually one of the few areas in the hospital that we deal with neutrons. But there is, neutron shielding is pretty effective if done right. So we rarely see them outside of the Linac vaults. But really, generally what you have slow neutrons and fast neutrons. They behave a little bit differently. Slow neutrons are going to be captured by a nucleus to interact with. When they're captured by that nucleus, generally they'll kick off a gamma. But then you're also left with a radioactive atom usually. So you have a stable nucleus that absorbed this neutron, so it's now in an unstable state, and it most likely will decay at some point. Now it could decay quickly if it's a short-lived isotope, or it could decay much more slowly. It's common for linear accelerators that have been in operation for a long period of time to have activated parts. A lot of the metal in the machines can start to have cobalt-60 in them, because stable cobalt is a common part of stainless steel. So when you have stainless steel that is in a large neutron flux, it will eventually become activated. And because cobalt-60 has a 5-year half-life, it activates faster than it decays. So there's some buildup of this activity. It's not a very high activity, but it is enough that you can detect it with an instrument. Neutrons can also kick out an alpha particle, or with the right isotope, something like uranium-235, the neutrons can be absorbed through the nucleus and then split, and that is a fission. Fast neutrons generally do not get absorbed by the nucleus. They sort of just bounce around. I've heard the analogy of Super Bowl. They kind of just bounce, slowly losing their energy. They mostly lose their energy to materials that are high in hydrogen, something like water. A lot of plastics have a high hydrogen content, and the reasoning for this is that if you think of a neutron, a neutron is the same size as a proton, and so a hydrogen nucleus is a proton. So when a neutron and a proton hit, because they have similar masses, there's a more efficient transfer of energy from that neutron to the proton, so they recoil off each other. Contrast that with a neutron interacting with a lead nucleus. That is, much, much bigger. It has, a couple hundred protons and neutrons. So it will just bounce off that nucleus and carry on its way with almost all of its energy still intact. So that's less desirable, because you ultimately want that neutron to lose energy inside the vault, and eventually be absorbed by the shielding, so it doesn't get out of the vault and then give dose to somebody who's working around the machines. There's inelastic scattering, which is that same process, except that there's also generation of some gammas in that. Neutron fluxes can be used in a lot of real world situations. It's common to have neutron beams that are used to find fissile material. If someone was trying to sneak a dirty bomb, or not a dirty bomb, but like a backpack nuclear bomb or something. You hear about these terrorist threats. The thought being that if you actually shoot a low flux of neutrons at, I think most commonly this is done to cargoes, the big cargo tankers that carry a lot of the big metal cases. The word's escaping me now, but essentially they're shot with a small neutron beam, and if you can detect actual fission events from that neutron, that would let you know that there is fissile material inside one of those cargo holds, and then it would be explored further as to exactly why that is, because that shouldn't really be happening. There's not a lot of U-235 being transferred around the world undocumented. So that would be a real reason to check it out further. So we talked about inelastic reactions. So fission, you have that one neutron that's absorbed by the U-235 nucleus, but it's very unstable, and it quickly splits into, generally doesn't split evenly. It splits a little bit, with one half being a little bit bigger than the other half. But you can see the release of two neutrons. So again, when we talked about that criticality, or that the chain reaction, is that if you have enough U-235 in a small vessel, those two neutrons can then go on to split two more U-235 atoms, which then create four neutrons that can then go split, and that's that chain reaction. So if not enough neutrons are actually leaving the vessel, then you can have the start of a nuclear reaction. Now fusion is a little different. That's, instead of splitting the atom, you have a combination of two atoms to create a new atom, essentially. Now each individual fusion event gives off much less energy than a fission reaction, but it's much smaller atoms, they're much less toxic atoms. You're left over with helium as opposed to many, many different highly radioactive fission products. So even though it would give off less energy per interaction, it's still a much better form of energy production. The only problem is that it's not used in any feasible way. There's still no real strategy for doing it in a way that you get more energy out than is put in to actually start the fusion reaction. So you always hear that fusion technology is only 10 years out, but it's been that way for decades. So who knows if we'll ever have a truly usable fusion reactor. Quick thing we'll cover is linear energy transfer. So this is a very important topic when it comes to actual biological effect of these radiations in the body. Now, every sort of photon or radioactive particle is going to have a different level of linear energy transfer. It can be very well documented how much energy they deposit in tissue over a certain distance. You can see keV deposited per micron. Around the 250 kVp X-rays, that's really where you have a sort of peak in the photon range. The higher energies are going to be less likely to interact. Then you see something like an alpha particle. They lose a ton of energy over a micron because they lose essentially all their energy in a couple of millimeters at most. So how does that transfer over to actual biological damage? That's what this factor called the RB, the relative biological effectiveness. So that is where lots of quality factors come from. That's where you have to take into account the type of radiation that people are exposed to change absorbed dose to effective dose or equivalent dose. And those are all concepts we'll get into a little bit later. But essentially, those mean that you're taking a physical quantity of absorbed dose and trying to translate into how much of an effect you can expect in a biological system, whether that's a patient or a victim of some sort of atomic bombing or a research animal. But the base of the RBE, it's relative to 250 kVp X-rays. That is an RBE of 1, and then everything else is based off of that. So the highest biological effect you can get is at an LET of approximately 100 keV per micron. So if you saw someone like an alpha particle, it can get to much, much higher than that. And you get to what's known as actually overkill, where a cell, because it has such short range, it actually won't affect many, many, many cells. It'll just affect only a couple of cells because it's depositing all of its energy in that range. So it's not always more energy, more damage. It's you hit a point where there's just too much damage over too short a distance to actually be more damaging. And then so this RB, this relative biological effectiveness, goes into different quality factors for different types of radiation to see how damaging they actually are in a real world setting. So that's it for this. There's another small presentation for this week. So just look through these two, and we will meet on Thursday just to discuss any questions you guys have and maybe tackle a radioactive decay equation just to make sure everyone's on the same page. So I will see you all on Thursday. Thanks.